And here's my presentation. Okay, let me also open the chat here so that I can see your questions. Where is it? Okay, here we go. All right, so recording is on and I am sharing my screen. So, well, this webinar is, let's say, the first webinar in the fall of this year. And because we are about to release the new version of Atena, I would like to, or the topic of this webinar should be focused on the new and latest development in Atena, not only in this latest version, but also I would like to briefly mention something we are preparing for the near future. Also, because there may be somebody who is, let's say, not so familiar with Atena, let me spend a few slides at the beginning to a little bit discuss about what we are doing. So this is what is shown on this slide. So here you can see also our motto, which is test your structure before you build it. Nowadays, we are extending it also to the version before you print it, because as I will be mentioning later on, we are developing also our software into the direction of simulation of 3D printing of concrete. So we are focusing on developing software and technologies for advanced modeling and simulation of reinforced concrete structures, starting for small laboratory experiments where we can even simulate the random distribution of material properties, as you see on the top left, up to some large-scale modeling of containments or even high-rise buildings. So why we think nonlinear analysis or nonlinear simulation of structures is useful in practice? Well, it can provide a deeper understanding into the structural behavior for design, but also it is important for the maintenance of existing structures. And of course, we should understand that it is not a replacement for engineering judgment or expert judgment, which is still important important part of any engineering work. But if I somehow describe a little bit the motivation why nonlinear analysis is useful, and for that we can look at where our knowledge comes from. Yeah, all our formulas that we are using is typically based, very often it is empirical, and it is based on experiments which are usually small experiments that can fit into the laboratory. Of course, we try to simulate also bigger structures, but still it is some experiment which is relatively small and quite nicely defined, but we want to apply it in practical cases. And there you see some very often the structures we are analyzing is not so clearly defined in terms whether it is a beam or plate. Sometimes it is a quite combined situation, some parts embedded inside concrete, like you see here, or we have some very fancy architectural shapes where immediately all the formulas which are working well for nicely defined situations like beams and shells do not work so well. Like you see this pavilion from the Expo 2022. And nowadays also we have this new technology of 3D printing, where again the structures can have very complicated shapes. In addition, they are built by layer by layer. So, and in these cases, also these traditional formulas are not easy to apply. And that's why nonlinear modeling is a good way how to check and how to supplement our traditional methods. So our software is based on finite element method. So if I slightly or very briefly summarize what it is about, basically we divide our structure into finite elements, and inside each finite elements we have integration points where we are evaluating the stresses, and these stresses are normally calculated from strains just by elastic predictor. But in reality, we can have cracks that develop, or concrete crushing, or reinforcement yielding. So we have this corrector phase. So if we look about the response of the structure, there is always a first, we all divide our loading into steps. And the first part is always a predictor where we assume more or less elastic behavior. And then we have this corrector. So it is an iterative process, and we need to satisfy the equilibrium. Well, very briefly about the models that we are using. So we are using this fracture plastic material model, which is based on decomposition of strains into plastic part and fracturing part. For tension, we are using this Rankine type of model with softening in tension based, and the softening is based on the crack band method. And similar approach we are using also in compression. And in compression, we are using the plasticity-based model, which has the hardening part and the softening part. And again, to highlight, we are using a fracture and mechanics-based approach for the softening. That means we assume that there will be some kind of crash band on which we can, let's say, integrate the plastic strains to calculate, to evaluate the slope or the softening behavior. Of course, we need to validate. I'm not going to spend too much time on this because I have already shown this many times. Those are some validation cases in history. This is the famous Toronto beam. I'm showing it because I want now to show some newer results. So this was the Toronto beam where we had a very nice prediction, and we were the winners of this competition. But now there are, or not now, but last year, there were two interesting competitions I want to mention. One was, actually both of them were organized by University of California in Berkeley. And first one was a similar beam like this Toronto beam, where you can see our predictions here. There were actually two tests. One was without shear reinforcement and one was with shear reinforcement. So our results here were very good. And that we, as you can see, we were in this 10% zone they call it zone of fame. But we understand that actually this is quite some luck involved, because to predict the concrete behavior in less than % accuracy is quite difficult. And let me then go to these newer experiments, maybe here, or these newer blind competitions. I will spend a little bit more time here. So as you can see, the first one was a very similar beam, it was, I think, around 90 meters span, 4 meters height, very similar one to the Toronto one. Again, they tested the beam such that one half was without shear reinforcement and the other part was with shear reinforcement. So when the first part cracked, they put these ties to strengthen it, and then they continued with the test to break it on the other side. And here you see the results. So this is on the left is with the lower strength indicated by this green line, which indicates the results from the experiment of the unreinforced part, and on the right you have the results for the reinforced part. And you can see our results this time. We quite under predicted the strength. And let me talk about it a little bit, yeah, so that I don't show only successes, or I can also show some problems. It is not easy to predict these behaviors. Well, behavior of these beams. So here, if we look first at this unreinforced case, you can see that we are, let's say, 50% below. which would look very bad. But on the other hand, we have to understand that this is only the load, additional load. But first of all, the beam has a significant self-weight, which is even higher. Let me show it here. Yes, you see the strength was about 100 and the 100 kips, and the self-weight was 116 kips. So that means the load or the on that the beam was subjected to just by self-weight is 50% of the load existing on the structure. So if you consider that you see that the results come to about 25 and 22% error, which of course is still not very good, but we know that one can easily to predict from other papers or from some uncertainty modeling that we did in the past. We know that for shear strength, the accuracy of numerical predictions is around 16%. This time it was a little bit higher, and the main reason was that I'm evaluating here again. This is the Toronto 2015, where our predictions were good, and this is these Berkeley situations where our predictions were not so good. And one reason for that was the shrinkage. We thought when we started this modeling, we thought that we should really have a very low strength, so we introduced also the the shrinkage into this. We estimated what kind of shrinkage will be in this beam. Of course, we were not really sure about the exact age of the loading, but this was the main reason why we so much underpredicted. So, for instance, you can see this. This is the experiment. Is the dotted line. Yeah, so that's, for instance, the lower one is here. And if we use the default Atena settings, yes, without any adjustment of material parameters, we would come up somewhere here. So already it would be close to this 16% accuracy I was mentioning. But of course, if we take out also if we then adjust, so these default parameters will be without any shrinkage considering. And if we then adjust some parameters, then of course we can obtain a perfect match. But this is of course easy to do. Once you know the results, you can always adjust something to have a good match. But the important, let's say, result from this was that the default parameters of Atena would have been the best to use rather than trying to make any adjustments and changes to well, not best, but better than trying to make some modeling adjustments that we did, unfortunately. So let's say what we learned from this was that the shrinkage was not necessary to consider. And then to really have a good match, we should increase the shear stiffness of the cracked concrete. Of course, the shear properties of cracked concrete is quite unknown. There are no clear rules for that. So this is, let's say, the freedom we have there, or also uncertainty in the material parameters in Atena, or basically in any modeling of concrete structures. So let me go to the other competition, which was organized also at Berkeley, but this time it was a column with cyclic load. Here you see the experimental setup. Here you see the damaged column at the end of the test. What is interesting in this column, if you look at the reinforcement, is that we have the stirrups are not distributed uniformly through the height of the column, but there are more of them at the bottom and at the top. I think the idea here was to consider a typical situation that occurs in United States in some older reinforcing methods for columns. Let me also open here Yes. Okay. All right. What we can look at the results here, and they reported the results, or how they were comparing the results was mainly by looking at the shear strength. So here were our predictions. Here, these bigger marks are represent the winners. In this case, also one of the winners from University of Austin, from Texas, was using Atena, and he was the winner in the student competition. And our prediction was not bad, but of course not as the best one. In the terms of strength, we somehow underpredicted the displacement at peak. On the other hand, I think many of the results, let's say, underpredicted or considered this more stiff. But very good prediction was in the ductility, yes, which was important. It was one of the most important parameters for this column, because the ductility is important for any seismic assessment. So in this situation, our results were quite good. Actually, Atena was used in one of the winning predictions in the student category. Here, just some animation of such a analysis in Atena. This was actually the analysis we kind of submitted. You can see the opening and closing of the cracks, the cyclic response, comparison with the experiment. As you can see, there was this initial stiffness was somehow higher, but I a little bit suspect that there might have been some problems in the experiment actually for this situation, because otherwise it makes no sense why there should be any reduction in the initial stiffness, because everything is quite clear and clearly defined. Okay, now this was, let's say, introduction to introduce Atena. For those of you who are not so familiar with it, and also I thought it would be nice to discuss these new blind benchmark results. So now let me summarize our latest development. So we are now releasing, and I think in the either end of this week or beginning of next week, we will release the new version of Atena 5.9.1. I will describe its features later on. But we are also working on a, let's say, new generation of Atena. We call it, so far it's an unofficial name, but we call it Atena 2023. And you can see the view of its user interface on the top right. So it is very similar to, let's say, window of Atena engineering. Those of you who also use Git, it is also, let's say, similar to Git, so that both of these families of preprocessors, we try to take the best from both of them. So it can be used to really model, as you know, in Atena, as you are familiar with in Atena, to model quite complex structural behaviors like this bridge on the slide. If you like, you can consider each reinforcement arrangement, pre-stressing, and all of that. And I will come to show a little bit more from this new version later on. But and then what I want to also spend a little bit more topic in my presentation today, because we continue very much on developing the software. So we are now using it, and I would like to show some examples of its application inside the digital twin approach, and also for the modeling of 3D printing of concrete. So if I let's somehow list the new features of the current release, so this, well, I would say there are no major changes. Yes, I told you we are preparing this major new version starting next year. So it is a little bit incremental improvements. I would say the biggest or most interesting improvement for the users would be some new licensing options, which also allows to have temporal licenses or software licenses so that you don't need to have a hard lock. And also for new users, there is a much easier trial version feature in this new program. As far as the functionalities, there are some new creep models for ACI and Canadian code, and also some new models for bond, which can take into account the aging or deterioration in time or due to temperature and corrosion. So that means the bond model can, or the bond model properties of the bond between reinforcement and concrete can degrade depending on the temperature, which might be interesting in fire analysis or because of corrosion. I will come to that corrosion. This has been already introduced in the previous versions, but I would like to show more examples of its application. Well, for the 3D printing of concrete, we are including now and extending the support for G-code. I don't know, for those of you who are working in or who are familiar with 3D printing, you know that in the end, once you have your CAD model, you have to use slicer to slice it into individual layers and create a so-called G code data file, which you then send to the machine, to the printing machine, and it basically then controls the printing. So we can now use this G code to actually control the activation of finite elements to simulate the printing process. There are some minor improvements in the post-processing Atena Studio. And another thing is that with the new version, we are also including the GID version 16. For those of you who are familiar with Atena, you know that this Git program is used as a preprocessor for Atena Science. And some interesting features in this new version is, for instance, a possibility to import a BIM format. For that, we are using the IFC4. IFC is the, let's say, international ISO standard for BIM data files. And also you can import G-code also into Git, into the preprocessor, and you can use it to help you develop actually the 3D model for concrete. And then also the G-code is used for the activation of finite elements. So now I would like to talk about these concepts of mainly long-term behavior and durability modeling in Atena. And for that, I will use this digital twin concept. What it is, let's say, a new way how also nonlinear simulation can be applied in practice. That is by combination or very close connection with the monitoring. So what is the motivation? Of course, there is some motivation to reduce the CO2 as it is now very popular. But of course, the biggest motivation is to make sure that our structures are safe and reliable. So when we model, I will show some examples of a bridge, which is a box girder bridge. And there you have various effects which can affect its durability. Because it is a bridge used by road, by cars and personal, by trucks and personal vehicles. There are some de-icing processes being used throughout the year. So we have chlorides which may penetrate to the structure, and And also they can leak inside through some insulation failures and problems, and then they can corrode also the external tendons. So we have developed recently a model in Atena where we can simulate the corrosion. How this is done, here are some examples from some experimental validation using a bridge from Japan. And as you can see, they took out the beams from this bridge, which were very much deteriorated. And that's why it was a nice way to validate the model, as you can see on these graphs on the right. So what we do, what is maybe most important, I will put, I will uh, mention or describe this graph on the top right, which is, let's say, the typical development of corrosion of reinforcement. Yeah. So first we have this so-called initiation time or induction time. That is the time it needs for the chlorides or maybe carbonation levels to reach the reinforcement depth. Once the reinforcement or the critical chloride concentration at the reinforcement depth is reached, we start to have corrosion of reinforcement. So as the corrosion progresses, we have more and more corrosion. At some point, due to the expansion, we have a cracking of the concrete cover, which again increases the corrosion. Then we have a spalling, that means the concrete cover is totally lost, and which again increases the corrosion rate, and then we may have a collapse of the structure. So we simulate this. Go, I have some better slide on this. Where's that slide? Oh, here. So we simulate this by a combined model where we have a finite element, three-dimensional finite element model for the mechanical part, where we can calculate stress, strains, and damage. And out of that also we obtain the crack width. And then we used a model for, first of all, to simulation the chloride diffusions, and then the reinforcement corrosion. And this is actually a one-dimensional model, while we don't need a 3D model. I know some people model this part also by a complex 3D analysis. But if you think about the typical situation, which I'm demonstrating on this slide, or on this figure, it is actually typically a 1D situation. Yes, we just need to know how fast the chlorides propagate from the closest surface to the reinforcement. And because in Atena we have the discrete model, or one of the options for reinforcement modeling is this discrete model. So we know for each reinforcement its distance from the loaded surface. So this means we can indeed use this one-dimensional model um, to model the diffusion of chlorides or carbonation. And once it reaches the reinforcement, the corrosion starts. And this model also considers the presence of cracks. So if there are some cracks, as you can see here, at this point, the diffusion of chlorides was faster and the corrosion started earlier, which is indicated by these red zones. This is the amount of corrosion. So we really can model quite effectively the corrosion rate of reinforcement, and this, of course, the effect is that the corrosion cross-sectional reinforcement cross-sectional area is reduced, and this, of course, then has an effect on load carrying capacity. Let me now go back to the presentation. Where was I? Yeah, I wanted to show you these two cases, two bridges. So where we apply this concept, one is a bridge in Czech Republic. It is with pre-stressing tendons. Actually, there are two types of pre-stressing. One, there are some bonded cables inside the walls. And then there were some external unbonded tendons inside the as you can see here on this cross-sectional view of the bridge, which are inside the box girder. And another bridge, this time it is only a reinforced concrete bridge. It is from Germany. And I told you that it is combined with this monitoring. So we use interesting monitoring system from Pechacher Consulting, which of course first needs to be calibrated by some predefined by some trucks with predefined weight, but then it can be applied on the bridge, and it consists not only from the sensors like strain sensors, as you can see here on the top right, but also there are some range finder using some laser scanner, laser beam, which can track the number of passing vehicles and also can track the number of axles and can be used to track the vehicle speed and so on. So this is, let's say, the typical result of such a measurement of one vehicle. So these red lines, they represent the strain readings. And as the vehicle is passing, it is detecting these peaks. This laser scanner is detecting them and can be used to calculate the axles, the number of axles, and the speed. And that means for each vehicle, you can get this kind of record, which shows the ID, the velocity, the number of axles, the weight of the bridge, I'm sorry, the weight of the vehicle. No, this is the weight of the vehicle. These are the weights divided per axle. This is the length of the vehicle. And then when you have all this data, you can obtain this kind of also statistical data. This is, for instance, showing the weight of the vehicle and the distribution in terms of some statistical graphs. And this one is, for instance, the time of the day and the typical speed that the trucks or vehicles are using when passing the bridge. Oh, there is one question from Evert van Vliet. So let me look a little bit the questions and try to answer them. Is corrosion calculation also possible underwater? Less oxygen. Yeah, that's a good question. I'm not sure if I can answer it right away. So, of course, those are the input parameters that we provide to the corrosion model. So basically, the main one of the important parameter there is, for instance, the corrosion rate, and I'll have to look at these equations. I don't have them in my head, but there basically you can define the type of conditions that you can use, and depending on the parameters that you select, you could simulate the corrosion underwater. But to tell the truth, I think right now the parameters that are, let's say, default there and you can select from, this does not cover. But I would expect that by appropriate choice of the parameters, you could simulate this situation as well. Okay, so I already mentioned that. So here are some results of this overloading situation. So here you can see the crack development, and you can nicely see how the cracks are very much affected by the position of these internal tendons. And here are some graphs or some videos or some animations of this loading process. So how does it work? So what we typically do, or how to evaluate the structural capacity using this durability model. Let me see. Okay, this may be the better graph to show it. But you may, okay, I'll show it here. Yes. So what we do is that we first load the structure until certain load level. Yes. In this way, we considered the, let's say, typical load acting on the structure to be the characteristic load, which is indicated by this dashed line. And then at this load, we consider the actually. I'm sorry. Here you see as the load was selected this level of the load combination. So this is not the characteristic load. I'm sorry. And it was let's say modeled that at this load level the structure will be standing there, and the corrosion or the durability model was used, which of course then causes. Oh, I know. I'm sorry. Here you can see it. Yes. So at this dashed line, at this dotted line. Yes, this is of course makes sense at the level of the self weight, at the level of G. Yes, because this is most probably acting for the longest time. So we load the structure first. Of course, we simulate also some pre-stressing and then loading to the dead load, and then you can see as if the structure, if there is no corrosion, we immediately continue with the overloading by the design load combination until failure. But if you want to consider the corrosion or durability model at this selected load level, which corresponds to the dead load, we let the structure stand for 50 years, 70 years, 75 years, which of course it is results here as a slight increase of deflections. This is the midspan deflection on the horizontal axis. And then at various times, at the selected times, that means 50 years, 75 years, 100 years, and 150 years, we overload the structure by kind of a virtual load test, considering the requested design long combination. And then we obtain some peak load. In this case, we reduced the peak to these points, which basically indicate when the concrete strain reaches 3.5 per mil, yeah, which is the typical design situation for concrete. And and then we can plot this capacity in time also. So that means for various times we obtain these peaks, and we can plot them in time, and we can obtain the evolution of the strength in time. So similar analysis was done in the other beam, for the other bridge. Here you see some typical results that you can obtain. So what this top one shows the chloride concentration. I told you that we consider some chloride concentration on the surface, but then the program plots here what is the chloride concentration at the depth of reinforcement. And then, of course, this results into some corrosion of reinforcement. You can see that where we have cracks, the reinforcement feels a higher concentration of chlorides, and of course higher level of corrosion. Here this shows the crack propagation, and this shows also the crack widths. So let me now go to this final picture. So again, for these two bridges, we can plot the evolution of their strength. If I come back here, this is again what I told you before. At each time, we consider overloading, kind of a virtual test, and we can then detect what is the gradual degradation of strength of the bridge. And here it is interesting to see how both bridges have a different level of degradation. Of course, the one with pre-stressing, where the pre-stressing is quite protected from corrosion, the effect is not so pronounced as for the reinforced concrete bridge, which at some point starts to degrade quite rapidly. Now let me go to this 3D printing. So this is also a new development that we did in Atena. And of course, you know, it is quite a popular topic nowadays. And one of the reasons why I think simulation can be helpful in this for the 3D printing is to prevent collapse of the structure, because depending on the printing speed and material properties, we may have a collapse of our structure even before the printing is completed, as you can see here on these photos. And also here are some results of the simulation. Of course, then the material parameters must be time dependent, and you can simulate and predict whether there will be a collapse, and then the printing speed or the shape of the structure can be adjusted. Because nowadays it is not such a big problem, because the structures that we are printing is typically small. So if we have a collapse like this, okay, they take it out and try it another time. But of course, once we start to use this technology for something more serious, I think this will be an important problem. That's why we are getting ready for that. So let me jump to the next topic because of the time. Of course, yes, I want to show you at least few slides from this latest version that I told you we are preparing. I want to emphasize this is not yet the version 5.9.1, which will be released this week or next week. This is, let's say, the new version, a totally new generation of Atena we are planning to release at the beginning of next year. And so I want to show one example, which is kind of a tram. And this shows the modeling, the environment, very similar to what you are used to. You define it by points, then you connect the points to lines. But the new thing in Athena, something you probably will find very appealing, and actually it is quite common in other softwares nowadays, is that you can, it will create a script file, a script definition in Python language. So later on you can reuse that to make some maybe parametric modeling. So the scripting is embedded directly into the program environment. So once you define the model, very similar to the definition in GID, as you remember it, then you define surfaces, then you connect, then you define maybe the rail, and then you extrude, very similar like you work, for instance, in Git. And you can define maybe some kind of simple structure like this. And what I told you here is that what is a new feature, and maybe a very interesting one, that you define this scripting language. So you can later reuse this scripting language by changing some parameters and generating various shapes of this structure. And then just what you know already in Atena, we have these nice definitions of materials with some helpful tools. For instance, here for the fiber reinforced concrete. And yes, I think I will not go to details here. I just wanted to give you some very first glimpse of the new version, what we are preparing, and some of the new and interesting features. Maybe one of the most interesting ones will be that it supports this scripting language. In addition, is that its data structure is really based on the BIM approach. So really, and the IFC or ISO standard for the IFC model. So you have every time you define some part of the structure, you actually identify whether it is a beam, slab, which can then help in the post-processing, also in the model development and definition of the material parameters. So with this, I would like to actually we still have some more time, so okay, so then of course once you prepare the analysis, you define the loading history. There you can see the various load, how they are applied. You can define the load combinations. You can easily follow how the various load combinations are being applied. And this is already what you know. Once everything is created, it prepares the input file. and this will be the same in the new version. You will use Atena Studio to run the analysis, and this is something you are familiar with. You run the analysis. This time it is this slab supported on a flexible foundation, and then you can obtain some modeling and simulation of cracking and the crack propagation. Okay, some video from the analysis here. So with this, I think I would like to conclude and my presentation, and we still have some time for questions. So if there are any questions. I don't see there is no question, at least not from the time being. I see that we still have some time, so I'm thinking whether there is something interesting I can mention. But yes, if not, of course, if some questions come up later, please feel free to send them to us. You can see our email on this last slide, and also our website. On the website, you can find a lot of information. I also want to mention to you that we maybe you don't know about, but we have this YouTube channel. Let me mention that to you if you don't know about it. If you go to a YouTube channel of Červenka Consulting, you can find the various videos, not only from some webinars, but also there is I'm now lost here, I'm sorry. But normally when you come here, you can also have a division into various normally they are divided into various categories, which divides them into I'm sorry, I will switch to this other view. Oh, here it is, yes. And to be sure, draw color as usual. So here is divided into tutorial sessions, Atena Studio videos, something for the first-time users, some webinars, or some interesting projects. So it can help you to navigate, and you can find useful information. Okay, so are there more questions? Okay, there is a question by Nigel Rees that he missed part about the digital twin. Well, as I told you, I'm not sure whether we covered exactly the topic that you are asking about, but we will provide you with the recording of this webinar so you can have a look and see the parts that you missed. Okay, there's a question when this version 5.9 will be available. Yes, the beta version will be available, as I told you, either this week or the beginning of next week. Yes. So it is already ready. We tested it internally, and now we will release a public beta version. And let's say after 1 month after that, there will be a full commercial version. So with this, thank you very much for your attention, and I will stop the recording.
Atena program produced by Chervenka Company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name Atena. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.